storage, thinking about, what type, maybe what chemistry of storage you're looking at. I kind of call this retrofit versus overhaul, and some maybe subtle nuances there. No conversation on grid tie battery backup would be complete without at least talking a little bit around AC versus DC coupling. Current product, I went a little light here intentionally because there's a lot of product currently on our shelves, currently in the pipeline that we'll be doing, product-specific webinars and trainings on over the next couple months. And then, of course, time for questions. So if that's clear, let's just jump right in. So why add backup? Why are customers asking for this? Why are we, as an industry, positioning this as a value-added solution for customers? It comes down to inclement weather and the fear of inclement weather. I think, year by year, we're faced with more brutal reality on, frankly, natural disasters and the impact on local grids that can have. Kind of tied into that, as grid type PV has become more popular, people have systems, people know people that have systems. The one critical drawback of grid type PV, and that's there in italics for emphasis, that one critical drawback becomes more widely understood. That drawback, of course, is if you've got a grid type PV system, basically anything except a Sunny Boy with a secure power supply, any typical grid type system in the event of an outage is not going to produce power. Of course, there's no storage there. So, think about a storm or a transformer going down, even a bright sunny day, no power available, even though you've got all that fancy equipment. So people are starting to understand that a little better. And as an industry, we've done a better job coaching people that this was going to happen. Programs and incentives for grid type storage continue to drive unit economics. What we mean there is self-consumption is starting to become more viable on its own. But, when you talk to a homeowner about we're adding batteries because we're gonna play a rate arbitrage and we're gonna do time of use and we're gonna eliminate demand charges, the natural follow-up is, oh great, and I've got backup power in case of a storm too. Well, maybe not. I think it's one of those things that if we add this application in and we do it smartly, we can sell solar plus storage to homeowners in a broader, more comprehensive way. So call that value stacking, call that benefit stacking. I threw in here an image from EIA, which is basically the intelligence and reporting arm of the DOE. And basically what we're looking at is electricity sales by sector in PREPA, Puerto Rico territory. So you see there the impact of the hurricanes on that market. And, if you think about, if these lines were to continue, think about the area under this curve as just, lost revenue for the utility, of course, but for the homeowner is lack of power. So there were loads there that are unfulfilled because there's no grid to draw from. I think that's the biggest selling proposition for backup is if that fear of an outage or a blackout is real or perceived, there's an opportunity to sell backup capability. So it could just be typical loads in a home, could be homeowners with unique needs around, medical equipment. We've heard stories over the years about people backing up pump and equipment for fish tanks, wine cellars, you name it. Sometimes it just comes down to, hey, would you like to keep your refrigerator running and some lights in the house in the event of a storm? Sometimes that's enough to put customers over the tipping point. Backup versus self-consumption. This is something I wanted to spend a little bit more time on. If you think about the use case for backup, it's an emergency fail-safe. It's the ripcord you pull on your parachute, so to speak. The battery is intended to stay afloat, as in a pure backup application, as the grid provides power and as your grid-tied system or not, net meters and supplies power to your loads and then to the grid. The battery stays full. I guess before the days of widely adopted self-consumption, there were lots of these systems out there that stayed at full state of charge, and the battery backup was there as an emergency source of power, rather than installing a generator Let's install a small system, let's install some batteries, and now we've got protected loads, and depending on the equipment, you might say a critical load panel. So in doing this, you've got to have a battery bank that prioritizes, call it depth of discharge over cycle life. You've got to have some chemistry that's specifically geared towards float applications. You're sizing the battery to both load power and energy. So because you're relying on the system to provide power to those backed up loads during an outage, you've got to have enough energy for the outage period. So we've got to think about what loads are we using, how long are they running, what's the total kWh, and we've got to think about the power as well. So what's the kW? If I'm backing up a refrigerator, lights, and a microwave, you know, I'm going to have periods during that outage where all three of those are going to be on at the same time. I've got to have an inverter capable of providing enough power that I'm not going to have brownouts during my blackout. Surge capability is definitely a consideration there. And most of the equipment that we see that's really suited to this application has that kind of headroom, has enough surge capability above continuous power ratings to be able to stand those surges. One other thing you've got to consider in a pure backup application is the switching time. Are you backing up critical power that needs, switching time in the 10 to 15 millisecond range? This would be, IT applications. This could be medical equipment. Most of us don't have those, I'd say, higher priority needs. Most of us are thinking about, can I get my switching times under a second? That's typically enough. You may have to reset clocks, but your major appliances are going to withstand that just fine. I'd say that the last part here on backup is what I would call introduction and complexity. You're introducing the talking point about load prioritization and how do we, what do we decide gets backed up? And somebody that I work with on a regular basis uses the term Sophie's choice the other day. So, if I've only got so much backup power capability, am I picking, am I picking lights, or am I picking my networking equipment? Am I picking that third lighting circuit, or am I picking my TV? Those are decisions that, you've got to counsel the homeowner on. So that's backup. In a pure self-consumption application, we've got a battery and we're intending it to cycle daily. So we figured out that there's the cost advantage for us to charge this battery, off of PV when power is abundant, and we're going to discharge it when PV is not present and power is expensive, essentially. So either that's for time of use or that's for demand-based mitigating demand charges. But we're intending to cycle that battery daily. So we're probably prioritizing, energy density and cycle life over depth of discharge. Again, we're intending to discharge energy to support the grid, not replace it. So we may not need, the same depth of discharge and call it current that we would need on a backup application. Switching time, not a consideration because we're not switching anything. The system is designed to backfeed to support our loads and possibly backfeed to the grid. We're not powering these loads off of battery. System will not operate in grid outage. This is the biggest thing, I think, when you think about how do you pitch a self-consumption. This is probably the biggest roadblock is if I don't include backup capability, they're going to have a great system. It's going to perform well. It's going to have all the economics. But in the event of an outage, what does the customer do? That's the biggest gaping hole. So we talked about these in approaching them from a pure play scenario. If I've got a pure backup application, if I've got a pure self-consumption application. We see now that most of the systems being installed where solar is incorporating storage are not pure plays. We're doing what we call benefit or value stacking, where we've got a system and it gives us a lot of column A and a lot of column B. We get some backup, we get the capability to support, call it short duration outages, partial home backup, and we've also got, the advantages of self-consumption. We've got a little bit more complexity in terms of sizing, but the system's not all that more complex on the production side in terms of how you design it and how you wire it. So let's talk about some of those design considerations. The first one, and I wanted to call this out right up front, is ITC requirements on how it will charge. So the tax credit for storage is tied to, what percent of the energy will come from the renewable production. So the call out here from Energy Sage, if your battery is charged with solar 80% of the time, you're going to take 80% of that, currently 30% ITC, and be able to offset that. If you are not planning to or can't prove that you're charging it from your PV system, then you're to be able to claim less of that tax credit. The other thing I wanted to call out here, and it's not prominent on the slide, but something to always take into account is you're able to take that tax credit on the storage component if the storage is installed at the time of, concurrently with the PV. So you're installing it all at once. In the event of a retrofit, the recent ruling is you can go back to that site within 12 months and do a storage retrofit. So great opportunity to, always keep a pipeline, if you will, of jobs that you've installed and gotten PTO within the last, call it 9 to 10 months. Gives you a 2-month window to go, revisit those customers, make sure they're happy, and have an upsell opportunity for a retrofit. Great consideration there when you're talking about, backup and how you design it, but also how are you selling it? How are you monetizing it? Next consideration here, what, if any, equipment are you keeping? I imagine in almost all cases, you're going to be keeping the modules unless they've got damage to them or they're just an extremely old vintage. So we're keeping that. I imagine we're keeping the racking. From there, it's a great question. I think the most likely tendency is let's keep everything and we're gonna AC couple the storage and we're only gonna add on what we absolutely need to. Sometimes that's the best way to do it, sometimes not. It's really gonna depend on the system, and we'll get into that, AC versus DC coupling consideration here in a short moment. Depending on how the system was designed and if it was kind of future-proofed, maybe this is easier, maybe it's not. And I say future-proof because there's some hybrid inverters out there that can run basically PV only, and you can introduce storage later. The best example of that is the SolarEdge storage product. I've got down here as the third consideration, loads. It's kind of like that real estate saying, it's location, location, location. On the load front, this is probably where you're going to spend a fair amount of time at the site survey and kind of final design stages. What are we backing up? What's the current? What's the duration? What's the energy we're going to need to plan around? And depending how you position the system to the customer initially, this is going to impact the cost of the project. This is going to impact what it looks like, how you price it, etc. And then the final thing, is this a cycling application? Is there a self-consumption application that we're trying to target around demand charge mitigation, around time of use rates, around SGIP, if you're in California? Or are we really looking at this as a pure backup application? So something that you got to take into account. We could probably spend 2-3 hours just thinking about design considerations, but the goal of these webinars is to kind of whet your appetites, get you interested, provide you with a bit of what and then give you a path to come back to us for a more detailed conversation, or to work with you on putting together bill of materials. So I want to feature here for a second a couple typical backup applications on DC versus AC coupled, and I haven't featured here what I would consider the third major application, which is an AC battery. We'll get into that in a second. In DC coupling, what you're doing is you're coupling, if you will, the storage and the PV on the DC array, on the DC bus, on the DC side of the inverter. So you see here, I like to keep these drawn with PV production on the left and then working towards the right, towards the grid, towards the main. So your array, because we are DC coupled, we're working through charge controllers, so our strings are shorter. We've got here 4 parallel strings of 3 in series to a PV combiner, into our charge controller. Of course, overcurrent protection here. On the out, we're coming out of this charge controller across the GSDI onto a common bus between the battery bank, the charge controller, and the DC inputs of your hybrid inverter. From here, we've got AC in, because remember, these wire up as a load. We've got AC in from the main panel, and then our AC output is this protected loads panel, where we're having the loads that we're backing up. So that's your typical DC coupled backup application. We've seen a ton of these systems. Hopefully this is not anything too revelatory for you guys out there. On the AC coupled side, so I've got here kind of a basic application of what we see for probably 70 or 80% of the AC coupled battery backup systems we look at. There's a lot of ways to deviate from this, but those ways are myriad, and we don't have the time to get through them. So working again from left to right, we've got our PV array. Because we're working with a grid-tied inverter that can handle much higher string voltages, array voltages, we've got here 12 modules in series, and you may have parallel strings here. We've kept it simple here with the small inverter. So your PV inverter on the output side, we've used a relay here, and I'll get into that in a second. We've got a connection here, the AC out of the inverter, to a production meter if required. I know they're required in my jurisdiction. To our protected loads panel, where we've got loads that are being backed up. The call it the input of this protected loads panel is tied to the output of our battery inverter. We're using the aux port on this battery inverter to trigger this relay, and I'll get into the controls on that in a second. We've typically got two inputs here on most of the battery inverters we're looking at here. So you may have a generator input, you may not. The AC input of this, of course, is tied to the load side of our main panel, and then we've got our battery bank across our DC bus to the inverter. So a couple things here. What are we using this relay for? So we're using this relay as an on-off switch, if you will, for our PV inverter. So when the system is grid tied and there's no outage, we're gonna, from our PV, we're gonna supply these loads first. Any excess production that's not needed by these loads is going to come to battery inverter. The inverter then makes the decision, do I need to divert power to keep the batteries charged, to cycle them or equalize them, or am I gonna export this excess power back to the grid? This is all well and good when the utility is running and there's no outage. In the event of an outage, this connection is effectively severed. So we've got, for all intents and purposes, an off-grid AC coupled system. So again, the PV inverter is going to harvest as much power as possible. This relay in normal state is closed. We're going to power these protected loads. We're going to send any excess production to the inverter. The inverter's got to make the decision. Do I have room in the battery bank to absorb this power or not? In the event the power is not needed in the battery bank, our battery inverter is going to send a signal to this relay to open, and our array is now offline. So the biggest drawback to an AC coupled system where you don't have active curtailment is it's possible to have a scenario where this battery bank cycles frequently. So what I mean by that is, because we've effectively got a PV inverter with an on-off switch and not a throttle, the PV inverter will continue to harvest wattage as long as it's connected to an AC source and as long as there's production. This becomes really difficult in an AC coupled system when the grid is out, because if the loads are not present, you've got basically a lot of current, a lot of wattage with nowhere to go. The best of breed AC coupled systems have some kind of communication between the battery inverter and the PV inverter to manage production in a more elegant or analog status. What I mean by that is, rather than having a 3 or a 4 or a 5 kW, PV inverter with only 2 states, on or off, if you introduce communication between the PV inverter and the battery inverter, you can have that inverter operate at 50% of rated power or 25%. You can curtail it up and down without simply turning the PV inverter off. The biggest drawback to turning the PV inverter off is that once you introduce AC power again, it's going to qualify that grid, and you've got a 5-minute count up, which, depending upon how you size the system and how much battery you've got, is really going to determine whether you make it to that 5 minutes or not. I've seen systems designed where the loads were not large enough to keep the PV inverter running during outages. The PV inverter shuts off, the battery inverter depletes the battery, and tries to animate the PV inverter again, but in waiting for the 5-minute count up, the battery gets to low battery cutoff. So the takeaway here, if you will, on AC coupled is call us at AE Solar. We'll walk you through this. We'll help provide you some options on looking at a curtailment solution, looking at providing feedback from the battery inverter to the grid tie inverter on how much to produce. If we can't do that, we'll make sure you size the system properly so that you've got enough battery to run the system at a steady state or at a sustainable rate during an outage. I've done a webinar on this topic, just AC versus DC coupling alone. That's available on our YouTube channel. If you need a link to that, send us an email. We're happy to send that out. Okay, so that was as brief as I can keep AC versus DC coupling. I've got more slides on that later. That's just an overview on kind of how the system goes together and the components. One thing I want to talk about at this point is partial backup versus whole home backup. And we've got a company out there that's really pitching whole home backup at what I would say is partial home backup price points, or giving the impression that it's, you know, a partial home backup kind of ballpark. So what are the differences here, besides just how much a load you're backing up, which is fairly intuitive? Partial backup, much more cost effective from the storage side of the equation. So if you're only looking at the bill of materials, it's much more effective because you're sizing that battery bank to your backup loads in terms of power, in terms of duration. Can be much more labor and design intensive. So the takeaway there is, if this is a retrofit, you know, you're moving loads around, you're creating a sub panel, you're rewiring things. You know, you're looking at a more intensive, you know, permitting and inspection process. Load selection is absolutely critical. So I've been harping on this throughout the whole webinar. Loads, loads, loads. What are we backing up? How much energy do we need? How much power do we need? And that, of course, you know, introduces homeowner conversations. That, you know, that choice of, are we backing up this or this, because we probably don't have enough energy to do both. So that's partial home backup. That's, I think, what we've traditionally seen out of this market, because storage has typically been the most expensive component in the system, and we haven't had a lot of good options for whole home backup. Getting to whole home backup here. So I wrote simpler on here, and I really struggled with that as I was putting these slides together. Simpler on a single line drawing, of course, simpler on a 3-line drawing. I'd say a lot trickier to pull off in terms of battery sizing and call it load control. So let me just walk you through the components here from our good buddies over at the Tesla company that drummed up a lot of excitement and then you know, kind of pulled back on the product front. So in a whole home backup application, we got a dotted line here around the PV because, you know, frankly, this is optional. It's not optional from the perspective of ITC, and it's, you know, for most of us, it's not optional because that's what we do every day is solar. But, you know, in theory, at least, this is an application that you could do without any PV. If you weren't concerned with how your battery was going to charge, if you weren't concerned about ITC or being renewable, you could run it this way. So basically, you've got, we're going to work from the right side to the left this time. You've got a meter. You've got I skipped over this. You've got a main panel. You've got loads. You're also introducing storage here, and you're introducing a backup energy gateway. So you need some way of effectively islanding the loads. because we're not islanding the loads via a sub panel or a backup panel, or some people would call that a critical loads panel, because we're not islanding them that way, we've got to island the whole house. So that's the backup energy gateway. And a lot of the different manufacturers that are in or getting into this space have a device of this sort in some form or fashion. It's typically a contactor that's activated either by relay or by a control board. In systems involving a generator, you might see an ATS here, but it's effectively a contactor that's going to close or open depending upon what we're trying to accomplish. As it's open, this system is now effectively islanded, and you've got storage, which in this case is an AC battery. It's got an onboard inverter, and let's be very clear about this. One Powerwall is not going to give you a whole home backup. That's probably the most disingenuous piece of these data sheets of all of this literature, is one Powerwall with 13 kilowatt hours of storage and call it 7 kW of continuous output is most likely not going to be enough for backing up a whole home without a lot more work on load shedding, on controlling loads, on keeping things from switching on. So in your typical, residential application, if you were to run this scenario and we either interrupt power or we experience a blackout, your home is going to continue to try to function the way it did before the backup event happened. So your thermostat is going to trigger when you get to a set point, and it's going to try to turn the air conditioner or the heating on. Your refrigerator is going to run. Your lights are going to run if they're turned on. All of these things are going to happen, either because they're programmed to do so, or because they reach set points, or because people turn them on. So you've either got to size this as an off-grid system and know exactly what you could possibly have running at any given time, or you've got to go through and you've got to throw load controllers on a ton of devices to make sure they don't turn on during an outage and overpower your battery. So, I probably should have put quotation marks around simpler here, because simpler in terms of components and wiring, but a lot more complicated in figuring out what exactly is going to run in an outage or in a backup event, and how do I size it properly. Lots to think about there with that one. And thus why, traditionally we haven't seen a lot of whole home backup requests, because they're just so darn hard to design around. Battery sizing. So we talked a little bit about, backup versus self-consumption. You would think that this would be very intuitive here, but it bears repeating. The battery needs to store enough energy to power the loads during periods of utility outages. So, typically I see installers that use a rule of thumb. We're going to size backup loads for 4 hours, because that's typically what we see here in terms of sustained outage. If it's longer than that, then we're going to try to run off of PV and storage, and maybe we supplement with a generator, maybe we don't. A much more important consideration here is the battery needs to be sized to handle the maximum charge rate. So I'm going to flip back to this scenario here. The battery needs to be sized to handle the maximum charge rate. So in the AC coupled system, we've got to size our storage so that it can handle the maximum amps coming from this PV inverter absent any load. So in the worst case scenario, if this is a 5 kW PV inverter and this is a Radian 8048, we've got to have enough battery here that it can absorb the 5 kW of PV that's got nowhere else to go before the relay opens and turns the inverter off. That can be a lot of amps. That's why most of the manufacturers out there, when you read the manual, they specify a fairly large battery, because they want to make sure that, in a scenario where you've got lots of production, no load, and nowhere for the power to go, your battery can absorb those charge amps. Critical conversation when you're talking about, especially when you're talking about AC coupling. The last part here, the battery needs to be able to support peak loads. So the first consideration we had here was sizing for energy. What's the total load duration? What's the outage time? Do we have enough kWh or amp hours? We've also got to be able to support the peak loads. Depending on your application and again what's running, I would think most of the time you're sizing to number 1 and number 2 first. In the event that number 1 and number 2 lead you to possibly a very small system, think about number 3 as well, because occasionally large loads will need extra current draw from that battery. Okay, so I'm going to come back to AC versus DC coupling, and I thought, we'll break up the slides a little bit with a system here from one of our customers. I don't recall where this is, but this is a really nice top hole mount with what I believe are the REC TP2 modules. So good stuff there. I didn't want to spend too much time on this, but there's a lot of conversation around DC versus AC coupling, and especially on retrofits. And I understand the rationale on AC coupling, and we'll get to that. I want to spend a little bit longer on DC versus AC coupling because I think it's really important when you're talking about retrofits. So that said, why DC couple? Typically, you see better communication between the inverters and the PV harvesting. And I put PV harvesting in quotes there because sometimes we're talking about PV coming into the system via charge controller. Sometimes we're talking about coming into the system from a PV inverter. The more you can get those things to talk to each other, the less you have to worry about uncontrolled charge currents, about sizing the system during outages, all of those things. We'll hit this on the next slide, but more efficient on non-concurrent loads. So if you are charging batteries at the time of production, this is a more efficient system. Wider array of available equipment and pre-wired solutions. That can be a very important consideration depending upon where you are, what you have access to, whether you are doing all of this wiring and configuration at the job site or back at your shop. Cons. Wiring can be expensive. So this is a consideration on what I would say are systems with ground mount arrays or where you've got the array not co-located with the power equipment. This is not lost on me that if you have a DC coupled system with with a 150 volt charge controller, and you've got a long run between the charge controller and the batteries, or the array and the charge controller. You're planning on voltage drop at 150 volts and not 600. You've got potentially long runs. Definitely, if you're dealing with a situation like that, you're definitely going to be on the side of AC coupling, just for the wiring savings alone. Less efficient during concurrent loads. So if you know that your loads are going to occur when there's no sun, you may want to think about an AC coupled system. Great flexibility on sizing an inverter versus array storage. So you've got the ability to decouple, if you will, and that's a horrible choice of words there. You've got the ability to break out, if you will, how you size the inverter, so how you size the kW portion of the system in terms of loads, versus how you size the array, versus how you size the storage. What I mean by that, let's go back a second, is these traditional DC coupled systems are very flexible in how you match up your array sizing to your battery sizing to your battery inverter. What I mean by that is it's possible to have a system with a really small battery inverter, a big battery bank, and a small amount of PV. If you are dealing with a situation where you've got really long outages you've got to plan around, let's say you're in Alaska and you've got to think about making it through the solstice. You're not planning on having a lot of PV, you're not planning on having a lot of loads, but you need a lot of storage. That's very easy to do with a system like this. The converse of that is true to a degree. Large amount of PV, large battery inverter because you've got concurrent loads with little storage need. That's feasible as well. On the AC coupled side of it, it's a little trickier to match the amount of PV inverter, grid tie inverter, and backup. There's much narrower tolerances, let's say, on how you size those three components. Let's talk about concurrent loads versus round trip efficiency. So top left, we've got an off-grid home in Wisconsin, where most most of our loads are concurrent with our production. Major loads being refrigerator, water, water heater, appliances, etc. So we see here the blue line is the loads coming off of this system, which I think is an XW. The yellow is the AC loads, and then the green is production. So we see a lot of overlap between these curves. We're not saving a lot of this power for later, let's say. This system on the bottom right is a system in Indonesia where almost all of the loads are outside of the production window. This would be a little more typical of a residential application where we've sized the, where the homeowner or the occupants are gone throughout most of the day. So on round trip efficiency, what are the losses in getting a watt from a module to a receptacle? And we've simplified this a lot. But when we're storing the power on a DC coupled system, we're running from the panels through the MPPT charge controller right into the batteries. So we've got 96% efficiency from panels to batteries. When we're consuming it, it's going through all of that wattage is going through PV from the modules through the charge controller into the battery, back out of the battery into the battery inverter, and then to the loads. So round trip efficiency of 88%. So if you're storing the power for later, more efficient to go DC coupled. If you're consuming it concurrently, not quite as efficient. On the AC coupled side, it's almost the inverse. We've got a two-stage conversion on the storage where we're going from the panel into the PV inverter, then into the battery inverter, then into the batteries. We'll call that 88%. On the consumption side, for concurrent consumption, much more efficient because you're basically just a grid tie string inverter at that point. So this is a consideration that sometimes gets lost on us when we think about what's the absolute best. And the way I think about DC versus AC coupling is, like tools in my shop. I've got a miter saw that I really like. I've got a table saw that I really like. They're not interchangeable. Sometimes you need one and not the other. There's no one size fits all. So why do people gravitate towards AC coupling? Much more efficient harvest and inversion for concurrent loads. Higher voltage bus, is going to lead to wiring savings between the array and the inverter. Easiest retrofits, and I think this is the biggest part on this grid tie battery backup retrofit webinar that we're doing here. When you're doing a retrofit, by definition, you're coming back out to a job site where there's equipment already installed. So sometimes this is equipment that's been there a long time. Given that our industry is, still somewhat nascent, that's probably not going to be the case in terms of long time. But there's equipment on site, and it just feels wrong in an industry where we talk about sustainability and renewables that we would consider, hey, take all that equipment, I'm going to put it in my truck and recycle it, and we're going to get you new equipment. That feels counterintuitive. You don't want to rewire things to go to a charge controller. You want to be able to leverage that grid tie string inverter if you can. Understood, and there's good options out there for doing that. If curtailment is enabled, can be a very elegant solution. So if you've got a way of providing a curtailment signal to the PV inverter from your battery inverter, can be a great solution. The cons: if you don't have that, you've got uncontrolled charge currents. So when you're islanded, you've got kind of runaway power to a certain extent coming out of that PV inverter. I say here, fewer approved options for storage inverter. What I mean by that is there's not a lot of good literature. There's not a lot of good solid understanding around which PV inverters can I AC couple with which battery inverters. It's a big gray area for a couple of reasons. One is some of the PV inverters maybe don't fully endorse this application because it can lead to more cycles of the relays inside a PV inverter. If you're using that PV inverter as kind of as an on-off switch to fulfill loads or top off batteries, you could be turning the PV inverter on and off multiple times a day. Whereas in a typical grid-tied net metered application, it turns on in the morning and it turns off in the evening. So we've seen some manufacturers be a little reluctant to fully get behind and endorse this application. The last piece here is reduced flexibility on system sizing. So I'm going to go back a few slides again. For some of the reasons that I elaborated on AC coupling around uncontrolled charge currents, around kind of system sustainability, we see a lot of manufacturers who have, guidelines or even I might say firm guidelines on how you size the battery inverter to the PV inverter. One manufacturer has a 1-to-1 kind of maximum threshold of 1 kW, or let's simplify here, 5 kW PV inverter for a 5 kW battery inverter. Other manufacturers have more of like a 3-to-4 ratio of 8 kW battery inverter, maximum 6 kW PV inverter. And what they're trying to control for is a situation with minimal loads, with high amounts of wattage coming off this PV inverter and nowhere for that power to go. Also, you've got to remember in this application, when you're islanded, this battery inverter has got to provide the grid and a stable waveform for a lot of wattage. Let's just put it that way. So this battery inverter has got to have enough, what I would call torque, to be able to create a stable waveform that keeps the PV inverter running, and is a nice clean waveform for all of your loads inside the home. So there's definitely some guidelines to follow there in sizing the two components to one another. What you really don't want to do is take your 14 kW grid tied PV system and throw a 4 kW battery inverter on there and think that the battery inverter is going to be able to create a waveform that keeps the PV inverter running. That is going to lead to really bad outcomes. So, spent a lot of time talking about application and got a little bit of time to talk about kind of what do we offer in terms of power equipment. The takeaway here is there's lots of options for doing this. On the DC coupled side, we've got good product from Outback Power, from Schneider Electric, from Magnum, from SolarEdge on DC coupled solar plus storage. So some of these are going to be more kind of your traditional off-grid and grid tie battery backup suppliers. Some of them are more well-known for grid tie and storage. Lots of good options there. I'd say if you're looking for more flexibility on sizing, sometimes you need a smaller system, sometimes you need a larger system. You're going to be looking from one of the top 3 companies there on the left. Some limitations on the SolarEdge product. You are a little bit kind of headroom constrained on supporting backup loads. There's just not a lot of headroom between the continuous output rating and the max surge rating on the SolarEdge plus LG Chem solution. Also no 3-phase options, no generator interconnect. Really just depends on how many options and features do you want in the system. On the AC coupled side here, so I focus mostly on the kind of the battery inverter or the hybrid inverter side of the AC coupled solution. So again, product from Outback Power, Schneider Electric. Those 2 solutions are going to require the use of a relay, or in the case of Schneider Electric, you can work with using the frequency shift to curtail the PV inverter. Magnum Energy's got a great solution out there using their inverter chargers and the GT600 microinverters, which can be a really elegant solution. SMA, of course, has the legacy Sunny Island product that's still on the channel, as well as the Sunny Boy storage that's launching here next month. Three sizes on that: a 3.8, a 5, and a 6, with 3 battery channels on each battery inverter. And then, of course, Enphase has a great solution for AC coupling that's almost an AC battery. So that's their IQ battery. And hearing some rumors that we're going to have a new Enphase battery solution in Q1, Q2 timeframe. So probably all I can say about that. But we look forward to that anxiously. So that's the battery side of the equation on AC coupled grid tie battery backup retrofits. On the PV inverter side, that's where you're going to need to do a little more homework and digging on, does that legacy PV inverter have means of taking a curtailment signal Is it approved for use in an AC coupled solution? Are you jeopardizing your warranty by installing it with the PV inverter? If you've got questions of that sort, come to us. We've got lots of answers, and we're happy to help you there. On the actual chemical storage part of the backup application, again, some of the considerations, you're going to need product that's comfortable with being in a float application. So something that hopefully has good tolerance for that, with kind of real low float amps. Some options here, we carry a full variety of Deca. So Unity 1, Unity 2. The Outback, I've got here on the upper right, the new PLC, right here on the right, the new pure lead carbon solution from Outback, and I'm hearing that there's a new battery coming out that may even actually be a little better suited to a backup application than the pure lead carbon. We see great stuff on the PLC in terms of cycle life, in terms of float life. So I'd recommend that as a great kind of across the board battery for any kind of solar plus storage application. I've got here featured as well the LG Chem Resu 10H, which you guys are probably familiar with, and then the Discovery AES, which is a drop-in lead acid replacement with lithium iron phosphate chemistry that is really hitting a lot of the applications that we're targeting well. So self-consumption, got backup there, good flow life, good cycle life. One thing that I did not touch upon is occurring to me as we end here is if you're looking at one of these solutions and you're trying to have the best of both worlds in terms of self-consumption with backup, you've got to think about if this is a battery that's being cycled for self-consumption, how much reserve do you program in for backup? I've seen typical applications using SolarEdge and LG Chem where 20% is reserved for backup kind of overnight. So you cycle you fill the battery up during the day, you discharge it during the afternoon and evening, and you're leaving 20% of that usable capacity for backup. If there's an outage overnight, are your loads backed up until the next morning when you can recharge from PV? That's real easy to do on some systems. It's a little harder to kind of think about in the design stage. And are you sizing your battery properly for cycling and backup? So while we've got the benefit stacking there, it could lead to a little more storage that you're going to need. Wow. So we ran through a lot in 49 minutes there. We've got a little bit of time for questions. Wanted to make sure I also got you guys the email address for AE Solar and our phone number. And then a little shout out to this guy. This is some stock photography that was taken a few years ago. And you see this guy and specifically this array on so many people's marketing pages. And I just want to give this guy a shout out because he's literally on like half the marketing documents in the industry. So cheers for this guy. Caitlin, do we have time and do we have any questions that have come in?